Gaia BH1 is the next known black hole. It is part of a very unusual binary system in which a star like the Sun circles a black hole that is 10 times the mass of the Sun. The problem with this finding is that it doesn't fit into the models that are already known about how stars and binary systems form and change over time. The envelope model and other ideas don't fully explain how the black hole could hold the star in place without destroying it. This event goes against long-held ideas in astrophysics and says that there are still a lot of things in the universe that haven't been found yet. A binary system is usually made up of two very heavy celestial things that are pulled together by their own gravity, like stars, planets, or black holes. At first glance, the newly found system looks like a normal binary system, but then facts come to light that leave experts stumped. Black holes about the size of BH1 generally move very close to the stars they eat. But the star that orbits this black hole moves in a path that is so wide and elliptical that the two can't be together. There isn't a theory that can explain why they are dancing in such a strange way. Gaia BH1 is about 1,500 light-years away from Earth. The Gaia project found the event. Since 2013, it has been tracking the locations, movements, and brightnesses of more than 1 billion stars in the Milky Way. Gaia's job is to make a very accurate 3D picture of the galaxy so that we can learn more about the Milky Way's structure, history, and growth. Gaia's search tools remove any strange events from the datasets in addition to making a general map of our galaxy. It was the binary scheme that caught their eye. If the black hole is what it seems to be, it has 10 times the mass of the Sun. The partner star is a G-type main sequence star, which means it is like our Sun. Its surface temperature is about 5,850 Kelvin. The star is about in the middle of the brightest stars in the sky. Scientists are still not sure what forces have helped these two stick together. There is no mass movement between the star and the black hole, which is very strange. The star isn't giving the black hole any mass that can be measured, and the black hole has only pulled the star close enough that it doesn't hurt the star. Gaia made the amazing finding, which shows how many great telescopes and observation satellites we now have to figure out everything about the universe. Along with NASA's James Webb Space Telescope, ESA's new Euclid Space Telescope is taking pictures of the universe that are very detailed. The European Space Agency is also working on the Gaia mission. Gaia is a satellite that was put into space and looks at our galaxy all the time. As part of their job, scientists are looking for both something normal and something strange in the world. Researchers can figure out the rules of the world by looking at structures that appear over and over again. Gaia BH1's strange feature could be the key to a whole new world of knowledge. At first, Gaia BH1 was thought to be a normal binary system, with two heavy items that are held together by gravity. Their gravity center is the same, and their dance in space looks a lot like the dances of many other binary systems at first glance. But it was clear that this wasn't a normal dance when the data was looked at more carefully. Once the companion star was known, it wasn't clear at first who the dance partner was. When experts learned about the black hole, they became interested in it too. It's interesting to see binary systems with stars and black holes because black holes usually eat mass, including stars. Many times, there is a balance of forces when they bind to stars without hurting them, like this. The black hole holds the star together just enough to let it go around. The star is still pulled toward the black hole, but not as much as it used to be. This often leads to very specific structures, and our science thought it knew just what conditions were needed for this to happen. That is until Gaia BH1 showed them that they didn't know everything after all. The star goes around the black hole in an irregular path that lasts 185.6 days and has a high eccentricity of 0.45. This situation is actually not possible in the real world. When the star is farthest from the black hole, it should be able to escape, but when it gets close again, the black hole should pull the star in. These things don't happen though. The star keeps going around the black hole in a safe circle. What holds them together if not one of the known physical forces? In the beginning, scientists thought that one or more other objects, like neutron stars or white dwarfs, might keep the two stable. But so far, none of the model's predictions have led to anything useful. Adding a third or fourth partner would likely make the setup less stable. The dance between the two was still a secret, and people were looking for answers. The next step was to see if the second dance partner wasn't really a black hole. But very specific changes in the star's path made it very clear that there was a black hole there. The waves, or wobbles, are like the fingerprints on an item. Both black holes and neutron stars have waves, but black holes' waves look very different. It was once again impossible to answer the questions. Scientists were interested in Gaia BH1 for another exciting reason. The binary system was found in space, far away from everything else. Researchers think there is something strange going on in this part of the universe because no normal model of binary evolution can explain it. Gaia BH1 is different from other envelope evolutions. Researchers are very interested in ideas, and when something new like Gaia BH1 appears, they need to find a way to explain it right away. When their favorite ideas don't work, heated arguments happen. Common envelope evolution, CE, is usually used to explain binary systems with close orbits. This model tries to show how the behavior of binary systems work. In the case of Gaia BH1, this model was used to figure out how the black hole and the star like the Sun got to be where they are now. Things did not go as planned though. The CE gives a general explanation of how a huge star, which is the ancestor of a black hole, turns into a red giant and grows very big. Then a partner star moves into the red giant's outer layers. Both stars are surrounded by this same cover. The orbits of the two items get smaller as friction and dynamic interactions make the system lose energy. The envelope is thrown out at the same time, and the last state is when the envelope is thrown out fully. A close binary system is all that's left. The star is usually a G-type star like in Gaia BH1, and the second object is either a stellar black hole or a small neutron star. Gaia BH1's orbit is too wide for the star that looks like the Sun to have been made by friction in a shared envelope, so this model doesn't fully explain it. The companion star is only about as heavy as the Sun, so it's not likely that it had enough power to completely remove the big envelope of the star that turned into a black hole. When two black holes are close to each other, mass is often moved from the companion star to the black hole. But there is no proof that this has happened with Gaia BH1. The explanatory method doesn't work at all in this case, and scientists don't know what to do. Our next machine, Gaia BH1, has reached the end of its useful life. According to the triple star theory, Gaia BH1 came from a triple star system that became dynamically unstable and broke up, leaving behind the system we see today. So, at the start of the system there were three stars, two heavy stars orbiting close to the inner pair, and a lighter third star, likely the G-type star, orbiting the other two stars farther away. It's possible that the two big stars in the inner system evolved faster than the star in the outer system. As supernovae, they blew up, leaving either a pair of black holes or a single black hole that was made when two of them merged. The growth of the dense objects inside made the outer star's orbit unstable. This is how things are now. There is a single black hole and a star like the Sun in a wide orbit around it. This idea about three stars might help us understand why the partner star is so far away. According to the common envelope evolution model, the G-type star did not have to enter a common envelope. This meant that it did not have to follow its rules. Overall, though, these triple systems are just guesses because the events that came before them can't be proven. Because of this, they stay just guesses. Triple star systems with heavy stars and very elliptical paths are usually unstable, but Gaia BH1 is not one of them. The triple star theory also doesn't answer all the questions, which is why it's not a good enough explanation. There is a lot that scientists still don't know about black holes and binary systems. Astronomy uses black holes a lot because they help us understand how huge stars change over time, how binary star systems work, and even where gravitational waves come from. But it's not always easy to find them and it's hard to learn them. Researchers use electromagnetic radiation as a source of information. What they find out depends on the features of the system and how active the black hole is. Strong radiation is made when active black holes pull matter from their partner stars. This radiation is mostly in the X-ray range. This radiation is made when matter swirls into a disk around a black hole and gets hot from the strong gravity. The name for these kinds of active binary systems with black holes is X-ray binaries. Black holes that are not actively consuming matter, like the one in the Gaia BH1 system, are known as inactive or quiet black holes. They are only recognizable by the way their gravity pulls on the partner star. They don't seem to be actively accreting matter. Astrometric data, like that from the Gaia project, can be used to figure out how the visible star moves and where it goes in space. But when it comes to black holes, the opportunities run out very quickly. There is a good chance that the unseen partner is a black hole if its mass is greater than 3 solar masses. To find black holes in binary systems, scientists also use gravity waves or the wobbles we already talked about. When two dense things like black holes merge, they send out gravitational waves. At the moment, LIGO in the US and Virgo in Italy are the only two detectors on Earth that can measure these kinds of waves. The best devices are used to measure these waves. On the other hand, wobbles are caused by the moving of a star that can be seen. Invisible companions pull on the star, making it shake a little. This is what happens with normal wobbles.